Yeah, thanks for the introduction. And hi everyone, I'm Hongbin from Duke University, and today I'm glad to present our paper, PoisonedEncoder, Poisoning the Unlabeled Pre-training Data in Contrastive Learning. This is a joint work with my colleague Jinyuan and my advisor Neil. Supervised learning is a well-known conventional machine learning paradigm. Given a specific task, for instance, traffic sign recognition, supervised learning requires manually labeling a large amount of labeled training data to train a classifier. Given another task, supervised learning will repeat this process again. So the key challenge of supervised learning is that it requires a large amount of labeled training data for each task. Contrast learning aims to address this challenge by leveraging a large amount of unlabeled data, which can be images or image test pairs. And these unlabeled data usually comes from the public internet, for instance, social media websites or Google search. Given the unlabeled data, contrastive learning aims to pre-train a neural network, which is called encoder. And a pre-trained encoder can be used as a general-purpose feature extractor for various downstream tasks. Suppose we have a pre-trained encoder. To build a downstream classifier only requires small amount of or no labeled training data. By analogy to the computer system, study the security of encoder is like the operating system level security study in AI ecosystem. Next, I will introduce more details on how to pre-train encoder and how to build downstream classifiers. Given an unlabeled pre-training image, we use data augmentations, for instance, random cropping and resizing of random horizontally flipping to create two random augmented views. We have an encoder, and we use it to produce feature vectors for each of them. Given another pre-training image, we will repeat this process again. The encoder is pre-trained in a way such that it produces similar feature vectors for two augmented views come from the same image, but these similar feature vectors for two augmented views comes from different images. Given a set of training inputs of a downstream task, we use the pre-trained encoder to extract feature vectors for each training input. And together with the corresponding labels, we build a downstream classifier by standard supervised learning way. And during testing time, given a testing input, we use the encoder to produce feature vector for it and use the trained downstream classifier to predict the final label. In our work, we find that the encoder in contrastive learning is vulnerable to poisoning attacks. And the attacker's goal is to make an arbitrary attacker-chosen image, for instance, stop sign image here. We call it target input, to be misclassified by the downstream classifier built on the poisoning encoder to make arbitrary attacker-chosen prediction. For instance, speed limit here. We call it target class. An attacker can achieve this goal by craft and inject the poisoning inputs to the unlabeled pre-training data. We note that most existing poisoning attacks are designed for supervised learning. And our poisoning attack aims to poison the encoder to make multiple target downstream tasks have attacker-desired behavior. In terms of our threat model, the attacker picks one target downstream task, for instance, traffic sign recognition, one target input, for instance, an image of stop sign, and a target class, for instance, speed limit. Our attack can be used to attack multiple target downstream tasks and multiple target inputs. More results can be found in our paper, and for the reason of simplicity, we default to use one target downstream task and one target input. Attacker's goal is to make the target downstream classifier misclassify the target input as target class. And in terms of attacker's background knowledge, the attacker has access to a few images from the target class. For instance, some speed limit images, we call them reference inputs. The key idea of our attack is to we formulate poisoning attack as a bilevel optimization problem, and then we use non-iterative heuristic solution to solve that. The first optimization problem formulates the attacker's goal. The attacker aims to find a set of poisoning inputs xp, which make the pre-trained encoder theta star pre-trained only clean inputs xc and poisoning inputs xp to make the downstream classifier produce the same prediction for target input xt and reference input xr. That means the encoder will produce similar feature vectors for target input and reference input. We sum them up and take average since we have a set of reference inputs. We note that the pre-trained encoder theta star already include another optimization problem that optimizes the encoder's weight theta by minimizing the contrastive loss. We call the first optimization problem and the second optimization problem respectively as outer and inner optimization problem. It is well known and challenging to solve this bilevel optimization problem by using statistic gradient descent, because every step of optimization for the outer optimization problem, we need to pre-train a whole encoder to solve the inner optimization problem. So we resort to heuristic solutions. Given a target input and a reference input, we create the poisoning input by either horizontally or vertically combine them. So when the encoder is pre-trained on the poisoning input, it will create two random augmented views by using random cropping and resizing. And the encoder will pre-train in a way to produce similar feature vectors for these two augmented views. And we note that at the same time it solves the inner optimization problem, which is pre-trained encoder. It simultaneously solving the outer optimization problem to make the encoder produce similar feature vectors for the augmented views from the target input and reference inputs. We called it approximately solving because augmented views are not exactly the same as target input and reference inputs. We noticed that such kind of combined images is maybe a real-world issue in the public internet. And next come to the evaluation part. We pre-train encoder using SynCRR and a pre-training dataset is Cypher10. And we also explore more pre-training algorithms and more pre-training datasets, including the full ImageNet. And this is a default setting. I will report in this talk's experimental results. And for building downstream classifiers, we use three popular downstream tasks and using the downstream classifier as a fully connected neural network. And the target input and target class are different for different target downstream tasks. And we randomly choose the reference inputs from each target class in target downstream task testing data. By default, we use 50 reference inputs, 1% poison rate, and 10 random experimental trials to report the experimental results. And we first want to evaluate the effectiveness of our attack. So given the target inputs and target class, we build the downstream classifier based on the poison encoder. If the downstream classifier makes the same prediction as target class, our attack success. Otherwise, our attack fails. So the attack success rate is a fraction of targeted misclassification for attacker. Our experimental result shows that our attack is highly effective across different target downstream tasks. We also want to evaluate whether our attack is stealthy by evaluating the clean accuracy and poison accuracy. Given the clean testing input, we first build downstream classifier based on the clean encoder, and its testing accuracy is called clean accuracy. We also build downstream classifier based on the poison encoder, and its accuracy is called poison accuracy. If ideally the poison accuracy is close to the clean accuracy, our attack is stealthy to the encoder provider. And we show that our poison encoder maintains utility, which means for each target downstream task, the poison accuracy is close to the clean accuracy. And we also explore three types of defenses against our poison encoder. They include pre-processing, in-processing, and post-processing defenses, which are respectively deployed before, during, and after pre-training the encoder. Due to the time limit, I want to conclude these defenses. We show that pre-processing defenses are either insufficient or ineffective. And we explore three in-processing defenses. They are effective, but will sacrifice the utility of encoder for downstream classification. And for post-processing defense, we fine-tune pre-training encoder for extra epochs on some clean images. We find that it's effective without sacrificing the encoder's utility. However, it requires manually collecting a large set of clean images. To round up my presentation, we find that contrastive learning is highly vulnerable to poisoning attack. An insecure encoder may lead to a single point of failure of AI ecosystem because they will impact the security of multiple target downstream tasks. And defenses are insufficient to defend against poisoning encoder. And thanks for listening. I'm happy to answer questions.